Hierarchy of Azure Structure. 1. Azure account. This is tied to your Microsoft identity. For example, someone at company.com. It's what you log into Azure with. This account can have multiple Azure subscriptions. 2. Azure subscription. This is a billing boundary and resource container. All services you deploy, VMs, databases, storage accounts, etc., are billed under a subscription. A subscription can contain many resource groups. A subscription defines quotas and limits, like number of storage accounts per region. 3. Resource group. This is a logical container for related resources that share the same lifecycle. You might have one for dev, one for prod, etc. It holds resources like VMs, storage accounts, databases, etc. 4. Storage account. This is a specific resource type for storing blobs, files, queues, and tables. It lives inside a resource group. It's tied to one region. It can host multiple containers, and each container can hold many blobs. Example in practice. Let's say you're working on a C/CD pipeline that uploads build artifacts to Azure Blob Storage. Your Azure account, DevOps at company.com. You're using a subscription named Dev and Test. Inside that, you have a resource group called C Infrastructure. In that group, you've created a storage account named Artifact Store Dev. Inside the storage account, you've created a container called Builds. And you push, zip blobs into that container via CLI or GitHub Actions. Azure Blob Storage. Imagine you're deploying a distributed application in the cloud. Your microservices are running in containers, your logs are streaming to dashboards, and your infrastructure is managed with IAC. But then there's a reliable, scalable place to store data, media files, logs, backups, C artifacts, maybe even training data for machine learning models. Enter Azure Blob Storage, Microsoft's object storage solution for the cloud. What is Azure Blob Storage? Azure Blob, binary large object, storage is Microsoft's object storage service, optimized for storing massive amounts of unstructured data like images, videos, documents, logs, or container layers. Think of it as S3 for Azure, your go-to place for anything file-based that doesn't fit neatly into a database. It resides inside Azure storage accounts and is organized into containers, which are like folders. Inside each container, you store blobs, which can be files of almost any size or format. Types of blobs. Azure supports 3 main blob types. 1. Block blobs, ideal for text and binary files. Common use case, storing documents, images, and backups. 2. Append blobs, optimized for append operations. Think log files or telemetry streams. 3. Page blobs, designed for random read/write access, mainly used for VHD files, for example, Azure VM disks. Tiers, storage optimized for cost. Azure Blob Storage has access tiers to help you optimize costs. 1. Hot tier, frequent access, higher storage cost, lower access cost. Cool tier, infrequent access, lower storage cost, higher access cost. 3. Archive tier, rare access, dirt cheap to store, but takes hours to access, great for compliance data. You can lifecycle manage blobs to move between tiers automatically based on age or access patterns. DevOps use cases. From a DevOps perspective, Azure Blobs can fit into many workflows. 1. C/CD pipelines, store build artifacts, container layers, deployment scripts, or Helm charts. 2. Logging and monitoring, push raw logs, telemetry, or audit trails to append blobs, integrate with Azure Monitor or ELK. 3. Backup and Doctor, use it to backup database dumps, VM snapshots, or Terraform state files. 4. IAC templates, upload ARM/Bicep templates or Ansible playbooks and pull them during deployment. Technical integration, you can interact with Azure Blob Storage through several tools. 1. Azure CLI. 2. Oz Storage Blob Upload Account Name Storage Account Container Name My Container Name app.zip file /app.zip. 3. REST APIs and SDKs. Azure supports .NET, Python, Node.js, Java, Go, and more. 4. Oz Copy, a fast and reliable CLI tool for large data transfers. 5. ozcopy./log/https:/accountblob.core.windows.net/container <SAS token recursive. Terraform. Resource Azure _storage_blob example. Name equals example.zip. Storage_account_name equals Azure _storage_account.example.name. Storage_container_name equals Azure _storage_container.example.name. Type equals block. Source equals path/to/example.zip. GitHub Actions or Azure DevOps can push/pull blobs as part of the C/CD workflow. Security and access control. Authentication. Supports Azure AD, shared access signatures, SAS, or account keys. RBAC. Integrate with Azure RBAC for granular permissions. Encryption. Data is encrypted at rest with Microsoft Managed or Customer Managed Keys, CMK. Private endpoints. Use Azure Private Link to ensure traffic stays within your VNet. Advanced features. Soft delete and versioning. Protects blobs from accidental deletion or overwrite. Blob snapshots. Immutable point-in-time copies of blobs. Event grid integration. Trigger workflows, like Azure Functions or Logic Apps, on blob events, blob created, blob deleted, etc. Static website hosting. Serve static frontends directly from blobs. Example architecture use case. Say you're building an internal artifact repository. You configure a container named artifacts in a storage account. Your C pipeline pushes build outputs, binaries, zipped apps, into it using a service principal with limited write access. Later, production servers pull the latest verified artifacts using a SAS token with read-only permissions. Meanwhile, you configure lifecycle rules to move older builds to the cool tier after 30 days and delete them after 180 days, keeping costs predictable. When working with Azure Blob Storage, it's easy to appreciate its flexibility and scalability, but beneath the surface, there are several important limitations you need to keep in mind, especially when you're designing systems that handle large volumes of data, automate deployments, or rely on high throughput. At the account level, Azure imposes some upper boundaries. Each standard storage account can hold up to 5 petabytes of data, while premium blob accounts cap out around 500 terabytes. Although these limits are generous, they're not infinite. If your infrastructure requires more, you'll need to scale out horizontally by provisioning multiple storage accounts across regions and subscriptions. Each subscription can support up to 250 storage accounts per region. When it comes to the blobs themselves, there are distinctions that matter. Block blobs, which are the most commonly used type, support up to 50,000 individual blocks. Each of these blocks can be as large as 4,000 megabytes, allowing a single block blob to reach a maximum size of 5 terabytes. For append blobs, often used for logging and telemetry, the limit is much lower, about 195 gigabytes in total, with each block capped at 4 megabytes. Page blobs, typically used to store virtual machine disks, max out at 8 terabytes and support random read/write access. Performance is another factor to consider, particularly in high-demand environments. For standard tier storage, you're looking at ingress speeds of up to about 60 gigabits per second and egress at roughly 50 gigabits per second. Premium blob storage offers much faster performance, supporting up to 50,000 IOPS and over a gigabyte per second per blob under optimal conditions. But hit these thresholds too often and you might experience throttling, manifesting as slow uploads, failed operations, or transient HTTP 429 or 503 errors during C/CD runs or heavy data ingestion. Access control also introduces some boundaries. While shared access signatures, SAS tokens, provide a way to delegate limited-time access to blob resources, they can become a security liability if left open for too long. Azure Active Directory provides a more secure alternative, but it only works with accounts configured with a hierarchical namespace. Additionally, when you're using advanced features like geo-redundant replication or soft delete, it's important to remember that each layer of protection comes with a cost, both in terms of pricing and operational complexity. Operationally, blob storage is designed to scale, but there are practical constraints. While containers can hold an unlimited number of blobs, listing blobs in very large containers can become slow or resource-intensive. Versioning and snapshots offer powerful rollback and audit capabilities, but they also silently increase your storage footprint and bill. Without lifecycle management rules in place, stale versions and unneeded snapshots can accumulate rapidly, especially in environments with frequent deployments or automated backups. In summary, Azure Blob Storage gives you a lot of room to grow, but it's not without ceilings. Understanding these limitations, how big your blobs can get, how fast you can move data in and out, how you control access, and how you manage lifecycle policies, is critical for building reliable, cost-effective, and scalable infrastructure. These constraints won't get in your way if you plan for them, but ignore them, and they can become silent killers for your automation pipelines and cloud architectures. When you create an Azure storage account, you choose a redundancy strategy. This determines how your data is replicated and protected against failures. Two of the most commonly used options are locally redundant storage, LRS, and geo-redundant storage, GRS. Locally redundant storage, LRS, Think of LRS as the basic protection tier. It replicates your data 3 times, but only within a single Azure data center in a given region. This is done synchronously, ensuring that every write is committed to all 3 replicas before confirming success to the client. If one server or disk fails within that facility, the other copies are still intact and can serve the data. However, LRS doesn't protect you from data center level disasters, like a fire, flood, or complete regional outage. So while it's cost-effective and perfectly fine for dev/test environments or non-critical workloads, it's not sufficient for production data that requires high durability in the face of regional failures. Geo-redundant storage, GRS. GRS steps things up. It not only stores 3 copies in the primary region, just like LRS, but also replicates those 3 copies asynchronously to a paired secondary region, hundreds of miles away. So now, your data is effectively stored 6 times, 3 in your main region, and 3 in a different geographic location. This is critical for disaster recovery. If your entire primary region goes down, Azure can initiate a failover to the secondary region. However, that failover isn't automatic. You have to trigger it manually, unless you're using RAGRS, Read Access GRS, which gives read-only access to the secondary region at all times. There is a caveat. Because the geo-replication is asynchronous, there's a slight chance of data loss, typically a few seconds, if a regional disaster hits before replication catches up. Still, for many production-grade systems, especially those storing backups, logs, or regulatory data, GRS is a must. In practical terms, if you're setting up Terraform scripts, ARM templates, or Azure CLI commands to provision storage accounts, specifying the redundancy level is a one-line configuration, but with huge implications for your reliability posture. For example, critical logs, long-term backups, or customer-uploaded files should go into a GRS account. Meanwhile, ephemeral C/CD artifacts or test build outputs might live happily under LRS. In Terraform, you set the redundancy level using the account_replication_type argument. It can be LRS, GRS, RAGRS, ZRS. In Azure CLI, the redundancy type is passed via SKU. The SKU defines both tier and redundancy via _.example. Oz storage account create. Name example /. Resource group my resource group. Location Eastus. SKU standard _GRS. In an ARM template, redundancy is specified using the SKU.name field. Azure offers multiple replication strategies to help you balance between cost, availability, and durability. You specify this in one line of code or config, but it drives how Azure protects your data from hardware failures, data center outages, and even regional disasters. Let's break down the 4 main ones. LRS, locally redundant storage. What it does: replicates your data 3 times, triple copy, within a single data center in the selected Azure region. Use case: good for cost-sensitive environments like dev/test, internal tools, or temporary storage where full disaster recovery, Dr., isn't required. Limitations: if that data center suffers a catastrophic failure, for example fire, flood, regional outage, you risk total data loss, no cross-zone or cross-region protection. In a nutshell: cheap and fast, but no protection beyond the building it's in. GRS, geo-redundant storage. What it does: replicates your data locally in the primary region, 3x, and then asynchronously copies it to a secondary Azure region, another 3x, so 6 total copies. Use case: great for production workloads where you want Dr. capability across geographic regions. Limitations: the failover to the secondary region is manual and only available in a disaster recovery scenario. The secondary copy isn't directly accessible during normal operation. In a nutshell: Africa emoji, safer for real-world disasters, but you can't read the backup unless you initiate a full failover. RAGRS, read access geo-redundant storage. What it does: same as GRS, data is stored in 2 regions. But with RAGRS, you can read the secondary, replica, region at any time. Use case: perfect for read-heavy, globally distributed apps, backup monitoring, and analytics. You can serve read traffic from the secondary site, or use it to verify backups. Limitations: still no automatic failover. Also, writes always go to the primary region, so latency for writes doesn't improve. In a nutshell: GRS plus passive read access, good for high availability reads and data redundancy with global reach. ZRS, zone redundant storage. What it does: replicates your data synchronously across 3 availability zones within the same region. Use case: Excellent for high availability apps that need 99.999% uptime, low latency, and protection against zone-level outages without leaving the region. Doesn't protect against region-wide failures, for example when the whole East US region goes down. In a nutshell. Triple replication across zones, durable and always available within one region. When to choose what? LRS, temporary files, dev/test environments, short-term storage. GRS, production workloads needing disaster recovery, for example backups, databases. RAGRS, global apps needing regional read access, for example CDN failover, analytics. ZRS, mission-critical apps where availability within a region is key, for example AKS, web APIs, low-latency services. Azure networking. When you deploy applications in Azure, you're not just spinning up virtual machines or containers, you're also building a network. This network determines how your resources talk to each other, how they reach the internet, and how traffic is secured and controlled. Azure provides a rich suite of networking services, designed to mimic a traditional data center, but in software, with global reach and cloud-native features. The core of it all, virtual network, VNet. The foundation of Azure networking is the virtual network, or VNet. Think of it like your own private LAN in the cloud. You define its IP address space, with CIDR blocks like 10.0.0.016, and then carve it into subnets to organize your resources, one for web servers, another for databases, another for your AKS cluster nodes, and so on. Each subnet isolates and routes traffic between resources according to your design. VMs, containers, and even some PaaS services like Azure App Service or Azure SQL Database can sit in a VNet or be privately accessible from it. Private networking, firewalls, and access control. You control access at multiple layers. 1. Network security groups, NSGs, are your firewall rules at the subnet or NIC level. They control what traffic is allowed in and out, based on IP, port, and protocol. 2. User-defined routes, UDRs, give you precise control over traffic flow, useful when inserting network virtual appliances, like firewalls or packet inspectors. 3. Private endpoints let you access Azure PaaS services, like blob storage, Key Vault, or SQL, through a private IP inside your VNet, completely bypassing the public internet. As a DevOps engineer, this is critical. You can build fully isolated environments, enforce least privilege access, and lock down traffic even during automated deployments. Getting to the internet, or not, Azure VNets are isolated by default. To reach the internet, you need a public IP address attached to a load balancer or VM NIC. To expose a web service securely, you'll typically use 1. An Azure Application Gateway, Layer 7, with SSL termination and WAF rules. 2. An Azure Load Balancer, Layer 4, for high-performance, low-level traffic balancing. 3. Or an Azure Front Door for global, geo-distributed web applications with intelligent routing and edge caching. To prevent outbound internet traffic, common in secure environments, you can set up NAT gateways, firewalls, or route traffic through a Bastion host or VPN gateway. Hybrid and global connectivity. Many real-world applications don't live in Azure alone. Azure networking supports hybrid cloud setups, connecting your on-premises network to Azure using 1. Site-to-site VPN, encrypted tunnels over the internet. 2. ExpressRoute, dedicated private fiber links to Azure, with SLAs and low latency. 3. FNet peering, connects VNets across regions or subscriptions with high-speed, low-latency links, without needing a VPN. For globally distributed services, Azure offers global VNet peering and private link to keep traffic secure and fast. Automation and IAC. From a DevOps point of view, everything about networking in Azure can be managed as code. Whether you're using Terraform, Bicep, ARM templates, or Azure CLI, you can 1. Define VNets and subnets. 2. Create NSGs and associate them. 3. Provision private endpoints and DNS zones. 4. Attach public IPs and load balancers. 5. Set up custom routing. Here's a quick Terraform snippet to create a VNet and subnet. Resource AzureARM_virtual_network main. Name equals metdev. Address _space equals 10.0.0.016. Location equals East US resource_group_name equals AzureARM_resource_group.main.name. Resource AzureARM_subnet web. Name equals web subnet. Resource_group_name equals AzureARM_resource_group.main.name. virtual_network_name equals azurearm_virtual_network.main.name. Address_prefixes equals 10.0.1.024. In summary, Azure Networking gives you the tools to build cloud-native networks that are secure, scalable, and programmable. Whether you're running a high-traffic web app, deploying containerized microservices, or lifting and shifting legacy systems into Azure, you'll rely on VNets, NSGs, private endpoints, and intelligent routing to make it all work. Let me know if you want diagrams, sample Terraform configs, or guidance on building specific topologies, like hub and spoke or zero trust networks. Azure Secrets. Let's talk about Azure Secrets from the perspective of a DevOps engineer, someone automating deployments, managing environments, and keeping production secure. In any serious infrastructure, secrets are everywhere. They're in your C/CD pipelines, Terraform scripts, application configs, and container environments. Whether it's an API key, a database connection string, or a password for a service principal, secrets are essential and dangerous if mishandled. That's where Azure Key Vault comes in. It's Microsoft's solution for managing secrets, certificates, and cryptographic keys in a centralized, secure, and auditable way. At its core, Azure Key Vault acts like a cloud-native safe. You provision a vault resource in your subscription, and it becomes the central store for everything sensitive. Your pipelines, scripts, or apps can fetch secrets securely at runtime, without ever hard-coding them. Instead of placing passwords in YAML files or environment variables directly, you store them in the vault, then reference them when needed. As a DevOps engineer, you're often working with automation, Terraform, ARM, Bicep, or even GitHub Actions. With Azure Key Vault, you can dynamically inject secrets into your deployments. For example, your Terraform script can fetch a secret, like a database password, at plan time, or your deployment pipeline can retrieve a client secret to authenticate against Azure AD, without ever exposing the value in logs or build artifacts. Azure Key Vault is tightly integrated with Azure AD, which means access is governed by role-based access control, RBAC, or access policies. You can grant a managed identity for your VM, app, or function access to just the secrets it needs, no more, no less. This lets you enforce least privilege with precision. From a security standpoint, secrets in the vault are encrypted at rest and in transit. You don't manage the encryption keys yourself unless you want to. Azure handles it by default, but you can bring your own keys, BYOK, for more control. Every read and write to a secret is logged in Azure Monitor or sent to your SIEM, so you get full visibility into who accessed what, and when. You also get features like secret versioning, expiration, and auto-rotation. If a certificate or password changes, you can rotate it centrally and everything that depends on it will see the updated version. No need to redeploy your app or touch a config file. This becomes crucial in regulated environments or when dealing with rotating service accounts and expiring tokens. In day-to-day DevOps work, Azure secrets are typically pulled using Azure CLI, SDKs, or REST APIs. They can also be injected into environment variables automatically when running on Azure App Service, Kubernetes with CSI drivers, or Azure Functions. You can even use Key Vault references in your ARM or Bicep templates to insert secrets into parameters securely at runtime. Ultimately, using Azure Key Vault for secrets isn't just best practice, it's essential DevOps hygiene. It turns secret sprawl into a well-audited, manageable process. It helps avoid costly breaches, ensures compliance, and makes your infrastructure automation safer and more scalable. Let's imagine we have the secret DB password in Key Vault. In Terraform data.azurearm_key_vault_secret.db_password.value retrieves the current version of the secret and injects it into the APS environment. In Azure CLI you can use the command ozkeyvault secret show. Vault name my key vault name. Name DB password. Query value. Output TSV. Azure Key Vault is powerful and secure, but like any cloud service, it comes with certain limitations that DevOps engineers should be aware of, especially when designing automated systems, scaling environments, or integrating secrets into C/CD pipelines. From a high-level architectural standpoint, one limitation is throughput and rate limits. Azure Key Vault has per-vault throttling, meaning that all requests, whether they're reading secrets, creating new ones, or listing items, are counted together. For standard tier vaults, the service is designed to handle around 2,000 requests per 10 seconds, with more precise limits depending on operation types. If your deployment process or app makes too many requests in a short window, especially during parallel deployments, you could get HTTP 429 too many requests errors. This is a common issue when large teams or systems hammer the vault during high-volume rollout events. Another limitation involves secret size. Individual secrets in Key Vault are limited to 25 kilobytes in size. This is enough for passwords, tokens, connection strings, and even small certs or keys, but not suitable for storing large files, SSH private keys with many comments, or binary blobs. For anything beyond small textual secrets, you need to use Azure Blob storage with restricted access instead. There are also soft limits on the number of secrets, keys, and certificates per vault, although these are quite high, around 1 million objects per vault. In practice, most users won't hit this unless they're auto-generating secrets or have thousands of deployments creating unique values over time. Still, if you're building systems at hyperscale, it's good to plan for vault partitioning or automation to clean up old versions. Speaking of versions, each time you update a secret, Azure stores a new version. There's no hard cap on versions per secret, but the accumulation of versions does count toward your vault's total object quota. Without lifecycle cleanup, version bloat can silently build up and eventually block new secrets from being created. On the network side, while you can restrict vault access to specific IPs or subnets, which is good practice, private networking with private endpoints is only available in supported SKUs and regions. Misconfigured firewall rules or region availability mismatches can cause unexpected delays or failures in automation. Lastly, Key Vault is region-specific. It doesn't automatically replicate secrets across regions. If you need multi-region availability, you must manually provision vaults in multiple regions and synchronize them yourself using automation. Azure doesn't currently offer cross-region sync out of the box. In summary, Azure Key Vault is a secure and reliable way to handle secrets, but it's important to understand the scaling constraints, network dependencies, object size limits, and operational quotas to avoid unexpected issues in production or high-throughput environments. Planning for these limitations early helps ensure smooth automation and compliance across your DevOps pipelines. Let me know if you want design patterns or workarounds for any of these challenges.